Okay, we're going to do a quick help video for solve rational equations. So please let me know if you have any questions, all right? Zooming in, what is the solution to the equation x plus 7 over 2 is equal to 5x over 3? All right, you might have different numbers, slightly different variables, but what we're going to use is a strategy called cross multiplication. We're just getting rid of the denominator from each side. So if I multiplied both sides by 3, the 3's over here would cancel, right? Because 3 over 3 is 1. If I multiplied both sides by 2, the 2's over here would cancel because 2 over 2 is 1. And by cancel, we mean it equals 1, and 1 times anything is itself, right? It's that thing. 1 times me is me, 1 times you is you. So we're going to use cross multiplication. What does that mean? I'm going to just take 3 times x plus 7. Notice the parentheses because it's the whole quantity, not just 3 times x, which is a common mistake. 2 times the whole thing, 5x. So again, we're doing multiplication. We have some variables, we have some coefficients or the number parts, and we have some constant terms. So right here, we use what's called the distributive property that states 3 times x plus 7 is the same as 3 times x plus 3 times 7. So 3 times x stays just 3x. 3 times 7 becomes 21. So we get 3x plus 21. Those are equivalent. Over here, we have 2 times 5x. 2 times 5 times x. Well, 2 times 5 is 10. And times x, we just keep the times x there. It can't go away. We can't just get rid of it. But it's multiplication, what we're doing. We're timesing. So we just did 2 times 5, and we got 10x. Perfect. Whenever you're solving, you want to get the variables to one side, usually. So I see this 3x, it's an implied positive 3x, so I want to do the opposite to get rid of it. I'm going to do the whole thing, not just the 3, the 3x. What a great question, right? I saw that wonderful thinking today. 3x minus 3x, subtraction, you're taking away the exact same thing, so you're going to get 0, and that's good. We want that. So then we have 21 is equal to 10x minus 3x, you're going to get 7x. The x's don't cancel all the way because you have 10 of them and you're only taking away 3, so you have 7 x's left. Over here, they canceled all the way because you had 3 x's and you took away all 3 x's. So then it's a 0. We just don't write the 0. Now we're going to divide both sides. Y, 7 times x. And division is the opposite of multiplication. We're trying to take away what's happening to the x to get it by itself. So you're often going to do the opposite or the inverse operation. Okay, we picked 7 because 7 divided by 7 is 1. And again, we don't write it because it's the identity property for multiplication, so we don't need to write it. 0 is the identity property for addition, so you don't need to write it. But now, 21 divided by 7, that gives you the final answer for x. Did you say 21 divided by 7 is 3? Okay. Welcome to use a calculator, however you want to think of it. Again, you might have different numbers or slightly different expressions. The same steps, cross multiply, pay attention to the signs if you have a positive or a negative, right? Oh, we're going to do this one. Okay. Okay, here's question 2, variation 1. What are we going to do? We're going to cross multiply. So I'll get 9 times x plus 10 is equal to negative 3x times 12. So same thing that happened before. On this side, we use the distributive property, and on this side, we just multiply the number parts. This side just becomes negative 3 times 12, so negative 36. X, the x stays. We're all being multiplied. And multiplication is commutative, it's associative, which means you can regroup it, you can reorder it, and it will still be the same. That's pretty cool. The distributive property lets me know that it's the same thing as if I did the parentheses first, or if I distributed the 9 throughout the parentheses. So I'll get 9 times x plus 9 times 10, which is 90, right? So far, so good. Again, we're trying to get x alone. I see an x over here. So actually, you could bring this over. If, say, you don't like negative numbers, you could make it positive by adding 36x to both sides and then bring over the 90. But truly, it's probably faster to just subtract 9x, because I'm trying to bring the x's, the variables, to one side of the equal sign. The equal sign is powerful. As long as you keep it balanced, you're going to be fine. So 9x, take away 9x, 0. So we're moving it to the other side by doing the opposite. That's in a positive 9x. So take away a 9x, subtract a 9x to get rid of it. So then this side, we're just left with 90 is equal to negative 36x minus 9x. It becomes negative 45x. Check on your math, like integer addition and subtraction, because integers now have positive and negative numbers. The minus sign, negative sign, subtraction, they kind of work similarly. You could think of this as negative 36 plus negative 9, or you can think of it as negative 36 minus 9, just regular 9. Either way, you're going to get to the same answer. There are equivalent ways of thinking about it. If you want to think, I already have negative 36 of something, right? And I lose 9 more, or I need 9 more, or something, right? That negative 9, something's happening there. Now I need negative 45. So I don't know if that makes sense to you or not, but otherwise, feel free to use a calculator and watch your signs and how your calculator works. Division. Why? Because it says negative 45 times x. So I'm going to divide by the entire negative 45 by the entire negative 45. Once you plug that in your calculator, you'll see this cancels. Same thing divided by the same thing equals 1. So you're left with just x. 90 divided by negative 45 should be negative 2. You can plug it in your calculator. How did I think of that? 45 is half of 90. So that's what number sense popped in my brain. 45 is half of 90. Therefore, 2 is how many 45s are in there, but it's a negative, and at the top is a positive, so the final answer is going to be a negative. Negative 2. Haha. Moving on. Oh, well, there you go. If you go through the whole thing. J's. So let's go ahead. Well, you have that answer. Let's look at this one, because I haven't seen the Z. Oh, no, I did do the Z. Did I do this one? X? All right, we'll do the X's. What I would do here is actually plug in our solution set. So let's just take a look at negative 1. What I'm going to do is plug and chug. I'm going to see if negative 1 works. So I just replace wherever I see x with negative 1. Okay, so this is going to equal 2 over 1, so just 2, right? Did I do that right? Negative 1, 2, negative, 2 over 1. So that's going to equal 2. So now I need to see if that is true. So we have 3 plus 1 over negative 1. Well, this whole thing, 1 over negative 1, becomes just regular negative 1. Check it, see if that makes sense to you. So 3 minus 1 is indeed 2. Okay, so negative 1 is an answer. I'm now going to scroll out and see if maybe... Okay, great. So now I have negative 1 and 2, negative 1 and 1. Well, I know negative 1 is an answer. So I know I can check the ones there. So let's try 2. We have 2 plus 3 over 2 plus 2. When I plug it in over here, I get 5/4. Cool. Let's plug it in over here. So now I need 3 plus 1/2 is 3.5. Okay, so that simplifies. This simplifies to 1 and 1/4. 5/4 fraction simplification, that is not equal to 3.5. So no, it's not 2. Okay? Let's try 1. 1 plus 3 is 4. 1 plus 2 is 3 4/3. Okay? Ooh. Oh no, that doesn't work. Why? Because if we have 1, we have 3 plus 1 over 1, which is equal to 4. And they're not the same. 4 does not equal 4/3. So that's not an answer. That's not an answer. Let's go down. Okay, and so look at that. We're done. So you already checked 2. We checked it right here. Not an answer, so it's not that one. You already checked 1, so it's not that answer, so it has to be this one. So that is the substitution method when you're given a solution set of values, potential values, that your answer could be. You just check them. You plug them in to check them. That's a great strategy, and it's a valid strategy. In question 4, we're going to do it algebraically. So you could have done it algebraically. The same method we're about to use, you could have done in 3. Okay. M is our variable. They already tell you the extraneous values, or the values that cause division by 0 in your original problem. If m equals 0 in our original problem, we have division by 0 right here. If m equaled positive 1, we'd have division by 0 over here. So they already tell you that. That's nice. That's good. How do we solve this algebraically? Well, I like to get rid of any variable in the denominator. There's different ways to do this. I'm going to do it in this step method, where I just simply multiply through by the denominator to get rid of it. That'll bring everything up into the numerator, but because it's an equal sign, an equation, it's a little bit easier. It's a little bit nicer. So I see this first denominator is an m. So I'm going to multiply both sides by m. By m. Over here, I have to use the distributive property. I'll get 6m times 6 over m. Well, there's where the m's cancel. That's why I picked an m. I picked it so that when I multiply it through, I get just 6. Then I have to do m times plus 2, so positive 2, so we get plus 2m. Perfect. See, I got rid of the fraction on the other side. That's great. I like it. Over here, there's no m on the bottom, so I end up with just like m times m plus 3 over m minus 1. Why? Remember, if I multiply by m, it's like I'm multiplying like m over 1. Whenever you multiply by like a non-fraction, you can make it a fraction by making the denominator 1. Because anything divided by 1 is itself, just like anything multiplied by 1 is itself. Right? And then you multiply straight across. So there we go. And m times 1 times, anyway, keep that in mind. Well, I still don't want to deal with this fraction, so now I'm going to multiply both sides by m minus 1. This whole thing stays together, so those are going to cancel. But what you do to one side, you do to the other side, but we have to keep it together. See, with the parentheses, they help us. M minus 1. Okay, perfect. We're super close to being done. So now on this side, I just have, these have canceled now. So let me just box it. On the one side, I have m times m plus 3. On the left-hand side, I have m minus 1 times 6 plus 2. So I have to FOIL or use the box method, binomial times a binomial. Over here, I have a monomial times a binomial, so I'm going to use the distributive property. So first with this side, m times m plus 3. Well, it's going to become m times m, which is m squared, plus 3 times m, which is just 3m. Okay, equals. Over here, you're going to watch me FOIL. It's not like the variables aren't like the m is over here instead of over here, so it's going to be out of order, but that doesn't matter. FOILing, or the box method, is just a way to organize our multiplication to make sure we multiply each term by each term. It's using the distributive property twice is what it's doing. We just use it once, and then we use it twice. It's just a quicker way of doing it. So m times 6 becomes 6m. M times 2m becomes 2m squared plus 2m squared. Negative 1 times 6 becomes negative 6. Negative 1 times 2m becomes minus 2m. At this point, we can combine like terms. So this just stays, this stays. So 6m minus 2m, we'll rewrite it to 2m squared plus 4m, because 6m minus 2m minus 6 is equal to m squared plus 3m. This is the algebraic method. You could be plugging and chugging to see if things are good. Okay, well, let me scroll down. Oh boy. Let me scroll down a little bit. All right, so then let me zoom out. Oh boy, I'm going to rewrite this up here. So down here, m squared, we're going to subtract m squared, and we're going to subtract 3m. But we have to do that to this side. So let me write it for you. 2m squared, but I'm going to minus m squared, okay, plus 4m, but I'm going to minus 3m, right? I'm trying to get it to one side. And then minus 6 stays the same, but I have to do this to both sides, and now it's equal to 0. Okay, sorry for the mess, but you could see it over here. I'm trying to get rid of it, so now I need to do that over here. So over here, why? Why did I do that? I need to get all the variables to one side. That's always a standard procedure when it comes to solving for a variable. You know, I mean, you don't always. There's lots of ways to solve in math. It's just a good go-to method. Setting it equal to 0 for a quadratic, that's nice because now I can use the quadratic formula, I can factor, I can do lots of things. I see that it should be factorable, right? M plus 3, m minus 2. What did I just do? Magic? No. Patterns? Yes. Negative 6. I need to think of the factors. Negative 3 times 2 makes negative 6. 1 times negative 6, all those that multiply together, right? Well, in this case, I need it to multiply to negative 6, but combined to positive 1. So that means 3 and 2 are 1 apart from each other, so I can get to 1 at least. But now the sign needs to be right. Well, if I have positive 3 and negative 2, it multiplies to negative 6. But when I do 3 minus 2, I get to positive 1, which would give me my middle term. At this point, we have our solutions. We set each of these equal to 0. When m equals negative 3, does that make sense? If you don't, just set it equal to 0 and solve like normal. M plus 3 equals 0. Subtract 3 from both sides, and you'll get m is equal to negative 3. Same thing over here. M is equal to 2. So that gives us our solution set using that set notation, negative 3, positive 2. Those are the values that solve those equations. Okay, question 5. Super quick. Doesn't matter what variation you have. Let's go take a look at Ruben. All right, Ruben. Did all this beautiful math, factored for us, got us some solutions. X equals negative 4 or x equals positive 3. Right here, you need to check those for extraneous solutions. So let's go back to our original problem and check the denominator, the bottom. So this one is factored, and look, when we make x equal to 4, negative 4, we'll get negative 4 plus 4. So this whole thing will become 0. We can't have that. Oh, even over here, plus x plus 1 over x plus 4. When we substitute in x equals negative 4, you'll get negative 4 plus 4, which equals 0. We can't have that. Let's check the other one, 3. That'll be 7, that'll be 6. Nope, that's fine. That'll be 7, that'll be 6. So 3 is fine. So you're looking to tell Ruben, we can't do this. Negative 4 is an extraneous solution because it creates 0 in the denominator. Look how you to check both of them to decide if they both are extraneous, if there are no extraneous solutions, or which one. Okay, so again, check your x equals. You might have a different one. Look at the denominator, the bottom of the fraction, and substitute them in. If it causes division by 0 on the bottom, then it's extraneous. All right, good thinking, good watching. Let me know if you have any questions.